Hello and welcome back to AIAIART. This is lesson 7, one that I'm sure some of you have been very eagerly waiting for, because today we are looking at diffusion models. We are walking right up to the precipice of the state of the art and taking a dive into the models behind these famous and very currently hyped papers like Glide and, of course, more recently DALL-E 2 that are able to produce incredible images in many cases just from a simple text input. So today we're going to be diving into what exactly these models look like. We're going to be building our own very small toy model and trying to understand enough so that we can look at these new papers coming out and just dig in and feel like we understand what's going on, and we could do this ourselves if we had the time and compute. So if you haven't already, follow along by saving a copy of the notebook in your own drive so that you can make changes. And let's dive right in. Okay, so first of all, where do diffusion models fit within the larger zoo of images? This is from an excellent blog post that goes into the maths and theory behind diffusion models. But if we compare them to other models we've seen, so for example, in a GAN, we start with some noise. We have a generator part of the network that produces some output image, right, a fake image. And then we have this discriminator side that compares the real images from the training set with the fake images, and the generator tries to fool the discriminator tries to keep track of the differences, and in this sort of adversarial way, the generator gets better and better at producing plausible images from noise. And we said that this was really cool, but they can be quite finicky to train. They have various issues like mode collapse and so on, but still a pretty neat model type. We also saw autoencoder models earlier in the course very briefly. The idea here is that we're shrinking some input image down to a much smaller latent representation, and then decoding that back into the original image. And by training the encoder and the decoder to perform this sort of compression step, we get a decoder network that's able to go from a very small representation up to a full image. And the theory is that, especially with some tweaks, these variational autoencoder modifications, we can get one that produces fairly plausible images from anywhere in this latent space. Again, pretty neat models, but they have their limitations. One we haven't covered in this course is flow-based models. You can think of those just as a variational autoencoder, but instead of the encoder and decoder being learned separately, the decoder is the exact inverse of the encoder. Through some mathematical trickery, they sort of guarantee this. So another great class of models, but again, they have their own issues. And so with all of these, we have the generation step being effectively one pass through some complicated model, right? The generator in the GAN, the decoder in our autoencoders. So diffusion models kind of break this trend, and they do things in a very different way. And so that's what we're going to dig into. But just to give the kind of high-level bird's eye view, the core idea here is that we start with some image, right? This is from our training data, and we gradually add noise. So this image becomes less and less recognizable, up until some point where we've added so much noise that it's effectively just pure noise. We can't see anything remaining of the original image. And then we're going to try and train a model to undo this process, again, iteratively, gradually, right? So we slowly degrading the image, and then we have this denoising model that tries to undo those steps. So that core idea is fairly simple and hand-wavy, and in a lot of explanations like how DALL-E 2 works, that's about as deep as you're going to get. So we're going to actually now, okay, let's implement this. Let's dig into the maths of how we do these noising steps. And specifically, let's dig into what this magical model is that does the reverse. So that high-level picture is all that we need to hold in our heads as we go. If you are looking for extra resources, a great place to start is this blog post by the authors of Denoising Diffusion Probabilistic Models, one of the early papers that kicked off this current wave of interest in diffusion models. And the blog post has great illustrations and explanations, as well as some fancy sort of demos of what these models can do. So highly recommend having that open in another tab. But in the meantime, we're going to try and actually implement this sort of high-level picture and dig into the details and see what those actually look like. Okay, so that's our grounding. Let's dig in. So again, if you haven't already, make sure you're running along in your own copy of the notebook if you'd like to make and save modifications. And all this is doing here is setting up a couple of requirements to download the data and a few very small convenience functions. So this notebook's going to be trying to sort of hide as little away as possible. and you can always just click show code if you want to see what's going on behind the scenes. Okay, so we need some data to train on, and we're going to choose this CFAR10 dataset, really small 32 pixel by 32 pixel images. It's also one that's used in the demos for a lot of these papers. So quite a classic standard benchmark dataset, and this shouldn't take too long to run. Just downloads the images and shows a little grid of what they look like. We're going to see in this notebook that we'll have a bit of trouble producing anything recognizable, especially training in the short amount of time that we have. But if you'd like to try something a little bit larger of a data set where the images are also much more similar, I also include code here for an alternative data set, this celebrity faces data set. And right at the end of the notebook, there's a little demo of training that. But for now, we're going to stick with this really small, dinky little benchmark data set. And we're going to see these steps described in the papers one by one and implement them ourselves. Okay, so step one is this noising process, right? We said we're going to create our training data by starting with some image and gradually adding noise until after t time steps, it's pretty indistinguishable from noise. And so if we go and dig into one of the many blog posts on this or the original paper, you'll see that, first of all, how much noise we want to add is something that we determine, right? We set up a noise schedule or a variance schedule called beta or beta, I don't know how to say it. And that defines how much noise we'll add at each step. And in this case, we're just going to keep that linear, starting out by adding a very small amount of noise and gradually increasing to adding, a slightly larger but still fairly small amount at each step. And the key idea is that over many steps, this will add up. So this is the formula, and it might look a little intimidating, especially if you don't have a maths background. So our goal in this lesson, I guess, is to kind of pick apart things like this and say, actually, this is not too bad, right? It looks scary, but we can break it down. So this little n here, this little squiggly n, that's saying, okay, we're looking at a Gaussian distribution, a normal distribution, and we're going to have our mean be a slightly scaled version of our previous image, right? So if I want to go from xt minus 1 to x of t, this noising step q is what we're looking at. And we're saying we're going to keep most of the image, but we're going to add some additional noise whose variance is going to be determined by beta, right? So that's all that this is saying here. We're going to scale our original image, and this gather is just reshaping and handling dimensions for us. Then we're going to figure out what our variance should be by looking it up in our variance schedule that we've defined. And then we're going to generate some noise, and we're going to combine the mean with that noise scaled by the variance. So it looks pretty scary in the maths, but in the code it's not too bad. And we can run this and validate that it's working, visualize the images after 20, 40, 60, 80 steps, and see that sure enough this is doing kind of what we hoped it would. It's gradually adding noise, and the component that is the original image is fading and fading until we have virtually no trace of it left. Okay, so this is pretty great, but we are kind of doing this iteratively, like it's shown in this example here. We're going one by one for every time step, adding a little bit of noise. And this is fine, except that for training, we want to train the model to undo these steps. And we don't necessarily say we want to train it on an example that's step 317. We don't want to have to do 317 little additions of noise just to train one reverse step. And so a nice little refinement here would be to say, what if we could see what the image looks like at time step 80 without having to do 80 previous steps? And so this is just a reformulation. Luckily, some smart people know how to do the maths to summarize this. And again, we've got this formula. It's not that different from the other one, except that now we have this weird little pi symbol, aka cumulative product. And we can do that in PyTorch really easily. And now we're able to jump straight to time step 40 or time step 80, whatever we want, in a single go, right? And we demonstrate that again here. We're saying, instead of saying for I in range, 0 all the way up to whatever, we can just take some example spots and calculate in one step what x looks like at time t is equal to 20, given x at time t is equal to 0, right? So we can just do this whole operation in one go. And there's lots of writing about the reparameterization trick and so on that you don't really have to worry about. If you're interested in it, there is some resources that you can go and dig in. I guess the core idea here is that the only trickiness that comes when we're doing something like this, continually adding random noise, having randomness in your chain when you're trying to then backpropagate errors and use the whole automatic differentiation stuff with PyTorch, it can cause issues. And so the reparameterization trick is just a way of separating out the randomness part from the chains or paths, I guess, through which you'd like to backpropagate your errors so that you don't have any issues. So a little bit of fancy maths. You're welcome to go and read more into it and check out the original blog post or the one that had this big image earlier. Yeah, so if you go to this blog post linked here, he has the full derivations and everything if you are interested in the maths. But like I said, the code is not too bad, and it just means that now we can jump to any stage in this noising process and see what the noisy image looks like, which is going to be useful for training. Okay, so that's sort of step number one, right? We're doing our, the easy part, just adding a bunch of noise. Now we'd like to say, well, now we'd like to start training a model to undo these steps. And this is where a lot of explanations, like I said, kind of just hand wave away what that model is. But I really want to dig into it here because it's a useful class of model, and it also kind of helps explain what's going on and what's actually doing the learning in these diffusion models. So we want a model that can take in something that looks kind of like an image, the noisy image, and output something that's the same sort of dimensions, but in this case we're trying to predict our noise or how to fix the image. And so we've seen autoencoders that go from an image down to some representation and back out, and you might think, well, maybe that's a good idea, and that might work, but a lot of autoencoders that, like the variational autoencoders we looked at earlier, they lose exact pixel information, right? In this sort of compressing down to a smaller condensed representation, that's great for learning features, but that's not so good in that you lose, through operations like max pooling and so on, you lose the exact pixel information. And because we're trying to predict on a per pixel basis what the noise is that we'd like to remove, that's not ideal. So a solution is something called a UNet, right? This is first proposed, I think, in 2015 for medical image segmentation. And the idea here is that we still have this kind of convolution and downsampling path, but we also pass information along, just copy and paste or skip information from early in the network at these high resolution layers back up to the other side of this U, where it can be used in reconstruction, but it's also then being combined with information from these deeper layers. So this turns out to be a really useful architecture for all sorts of things where we need to make predictions on a per pixel basis. You'll see this for like image colorization, the de-oldify project, for example, and many, many other tasks where you just need to, for example, decide which pixels contain a human being or something like that. So we're gonna, let's maybe just run the code to define our UNet, check it in action, right? In this case, we have a modification where we allow it to also take in some information about what time step it's operating on. And then let's set this training, and then we can go back up and look at the code. But it's just because this training loop is going to take a few minutes, we might as well set this running, and then we can go back and explore what exactly is happening here, right? This diagram is kind of helpful, but we want to see what's going on, and we also want to see what's happened since 2015 in terms of like how people implement a UNet today. So let's dig in. Lots of scary code. I'm actually going to hide the form part of this. But you'll see these are all blocks that we can break down. So first little definition here. This is an activation function. Remember, we use the rectified linear unit activation function. Swish is kind of a fancier, smoother version. Gained some popularity a few years ago. We don't have to worry too much about that. Then this next section, time embedding. Remember I said we'd like to predict this inverse step in the noising process, right? It would help the network to be able to know whether it's dealing with a really noisy image, in other words, a really high time step, or it's nearly done in one of these really low time steps. And so we're going to try and take what time step T, and we're going to embed it in a representation that's useful to the network. And so that's what this time embedding is doing. Sinusoidal positional embeddings, you can go and look it up in a lot of the transformers. They use something similar, but the core idea is that this is going to take in your time T and spit out a nice embedding that we can feed into the network as so-called conditioning information. And we'll see how that gets added in later. Okay, then residual blocks, made popular in ResNets. Again, this is just a useful building block because you get your convolution and grouping and so on, but it also has this shortcut connection so that some information can take a bit of a shorter path through the whole network. Again, just a kind of classic building block. Same with attention. Remember from last lesson on transformers, attention lets these models selectively weigh different parts of an input. And in the case of a UNet, we can have attention, especially at the lower levels. It just means that instead of only seeing a small sort of receptor field from the main input image that's now being compressed down, it's able to attend to different parts of the image and use that to inform its output, right? It just means that the networks can, selectively pay attention to, no pun intended, different parts of the input. So yeah, seems to add a little extra bump of performance. And of course, just more parameters as well to learn things. Okay, and then now we're defining some sort of useful larger building blocks for the downward chain and the upward chain, where we're combining residual blocks, attention blocks, and so on. And also here, okay, we'll come back to middle block, upsampling and downsampling, right? So this is all just kind of convenient stuff to implement this kind of UNet architecture. The middle block is of interest because, like I said, we want to condition this network on T as well. And so in the middle here, we're combining the X, which has come down all the way through the left-hand side of that U, with our time embedding. So yeah, we'll see that in action in the actual UNet class. Okay, so with all those building blocks out the way, this is the actual core definition. And this is what you'd look at if you wanted to get a quick high-level understanding of what some neural network architecture is doing. And so you'll see we have some different parameters we can pass in to specify which layers have attention, how much channels there are, and so on. But if you go and read through this initialization here, you'll see it's just setting up that kind of U-shaped structure, right? We set up all of the downward path, set up our middle block, and then the second half going up. And then in the forward pass, this is sort of what actually happens when you pass data through the network. You can see we take our time step and we turn it into an embedding. We start with our image and then we feed it through the first half of the UNet, then through the middle block, combining in our T here, our conditioning information, and then back up through the second half of the network, and then through some final layers, right? I think they have a couple of extra ones right at the end just to get the output format nice and in the right range and so on. Okay, so that's our UNet definition. Quite a long little diversion there, but I just wanted to show that it is kind of something you can still approach and understand, right? It's made up of these building blocks that are made up themselves of smaller building blocks, and there's lots of literature on exactly why people do things the way they do, but the core idea here is that we just have this neat architecture that's able to learn some sort of high-level features by the sort of deep architecture of it, but at the same time kind of preserve some early high-resolution features and combine them together in smart ways. And the TLDR is that it takes an image and it produces an output, and this is going to be very useful for what we want, which is to take a noisy image and produce an output that is a predicted sort of estimate of what the noise is in that image. So with that UNet definition out the way, we can now see, okay, we can pass data that looks like a batch of images and a batch of time steps through the model, and we can get our output. So that all seems to be working, and we're ready to actually train. And hopefully this is already actually finished running, so we can see that it is working. But in our training loop, again, this is hopefully fairly familiar by now after past lessons. We are just doing, we're setting up our parameters. We know how to go, to a noisy image at a given time step. I've modified that function just to return the noise itself as well, since that's going to be our target. And then we're setting up our kind of bog standard PyTorch training loop, right? We're keeping track of the losses. We're setting some parameters like the learning rate. We are optimizing the parameters of our UNet network. And then within the training loop, we're zeroing the gradients. We're grabbing some images, right? Putting them in a batch. Then we are turning them into noisy versions based on some random time steps. And then we're trying to predict that noise. So we're passing the noisy images through our UNet. We're getting its predictions. We're comparing those predictions with the actual noise values. And then we're, that's calculating our loss backwards. Oops, optimizer.step. So we're creating some training data by noisifying, adding lots of noise to some input images, and then we're having the model predict the noise, we're comparing that with the actual noise, calculating our loss, and updating the parameters of our model to try and reduce that loss. And so that looks great. Over time, the loss gets lower. This is wonderful. So now we have our trained model, right? So now that's kind of big objective number 2 out of 3. We know how to add noise to an image. We know how to, excuse me, my mouse just did something funky. Yeah, we know how to add noise to an image. We know how to create a model that takes in a noisy image and predicts the noise. We've now trained that model on a bunch of noisy images. And we'd like to then say, okay, now I'd like to do the reverse. I'd like to actually generate some images. And to generate, what we're going to do is we're going to go from a bunch of noise, and we're going to apply this model a bunch of times, slowly removing noise from that image until we get something that's hopefully a plausible output. And so that's exactly what we're talking about here. You can go and read in the paper the algorithm for this sampling step, right? I think it's down here somewhere. And we're just going to convert this into code. And again, it's the maths can look a little scary, but we're saying we're using our learned parameters, right? That's what that little theta means, i.e. our UNet network. And we're going to, start with some random noise. And then we're going to run through our number of steps. And at each step, we're going to predict the noise. And then we're going to now do this kind of reverse step here to say, okay, given this predicted noise, I'd like to remove a little bit of that noise and move hopefully towards our final output image. And you'll notice there's some randomness in here. We're not just directly removing all the predicted noise. Instead, we're predicting the distribution of the noise, and then we're sampling from that distribution. Sounds kind of mathy, but you can read the code. It's not too bad. And if this all works, and if our model is trained okay, we should start from random noise, gradually reduce, and get an output that, well, it doesn't look exactly like anything specific. It at least looks much more like an image than the noise did. So it's doing something. Okay, so we can now talk a little bit briefly about why these aren't perfect image samples like those shown in the paper. And there's a few reasons. We can show that our model has learned something kind of useful by only going halfway, right? So applying 50 steps of noise to an input image and then trying to denoise that. And you can see that in this example here. We start with a noisy version of a horse, and then we get some kind of plausible, potentially images of a horse out. So the network is learning something, but it's not as good as the paper. And the simple answer is the paper trains it for, I think, like nearly, 10 and a half hours on a big cluster of TPUs, right? Equivalent to like 8 really high-end GPUs. So a little bit more training than our, 2 minutes that we did above. A minute and 42 seconds. So if you wanted to try and approach the paper quality, you need to train for a bit longer. They use 1,000 steps, or in some papers up to 4,000 steps rather than the 100 we used for demo. The models are about the same size, right? We can see the number of parameters in our UNet, or at least a rough estimate of it, with this little bit of code, and we can see 42 million parameters, pretty close to the 37 used in the paper. I'm not sure exactly what the difference is. I think maybe we're counting some extra ones that aren't actually trained or something like that. Everything else is fairly similar, but the paper just uses many more steps, trains for a lot longer. And if you'd like to see an example of training one that actually generates some outputs, you can skip to the end of this notebook where there's a little demo that sort of produces some faces. Or I also trained, just before the lesson ran, a few variants of this, just training a little bit longer, experimenting with some hyperparameters, and we'll talk about how we get this nice dashboard and these loss plots and so on right at the end. But you can see we actually kind of generate some semi-plausible faces. The CFAR10 outputs are still not super distinguishable as anything specific. But again, this was still trained in, half an hour or an hour and on very little samples. Okay, but we're now kind of coming to the end of our implementation of diffusion models, right? So we back up here. We've trained a model. We've seen that it does okay. We've talked about how we could make it better. So now the next part of this notebook is going to be moving away from code. We're not going to do too much more programming, but instead saying, well, okay, these things seem great, but they have some issues. And one by one, we're going to talk about those, and we're going to see how more recent papers have improved on that. Okay, so first big one that might be springing to mind is that when we actually want to make predictions, you might have noticed that even just making a few predictions took a little bit of time. In the paper where they use 1,000 or 4,000 steps, sampling a batch of images can take 20 seconds. It's not instant, and so this is the first kind of key limitation of these models, is that inference time, right? Generating these images, we have to run through all 1,000 time steps, and that is just really, really time consuming and compute consuming. And so there's been a lot of work on saying, can we reduce that? And you might think of some sort of fairly rough ideas like, oh, well, why don't we just, if we can predict the noise at time, t is equal to 50, why don't we just try and jump to t is equal to 40 by, using 10 times as much adjustment? And you can do that, and then actually, to be honest, if you read these papers, a lot of them are just refinements of that, right? They've got a lot more mathematical backing, and they've got some clever ideas around how exactly you sample, what time steps you want to use, how you scale the predicted noise, and so on. But the kind of core takeaway, we're not going to go too much into it. You can read the papers if you want. The core takeaway here is that through some clever tricks, we can go down from having to do 1,000 samples to taking a model that was trained on that number of steps, but doing some clever maths to kind of cheat our way into generating fairly good samples with much fewer steps, maybe 25, 50, 100 steps instead of 1,000. There's still a lot of active research in this area, right? You'll see new techniques coming out, but yeah, there seems to be like a sort of general consensus that we can at least, take an order of magnitude or two fewer steps and still get a plausible result. And if you experiment with this in some of the later notebooks, you'll see that they have, PLMS sampling or whatever. It tends to do almost as well as the full, incremental sampling. So just throwing that out there, that's our first problem. Sampling takes a while. Our first solution, there's some clever tricks to kind of skip a lot of those steps. Okay, don't want this lesson to go on too much, but now we're going to move through a couple of additions to these models, because so far we've talked about generating images, but we haven't talked about using text. So we want to talk about how do we make them better at producing images that we can actually steer, and then how do we do further refinements to make them faster. So the big one, guided diffusion, right? When we look at glide, we're looking at taking a caption and turning it into an image. Ditto DALL-E, really famous. Its key capability is this whole text to image step. So I think the glide paper is kind of the foundational one there compared to DALL-E 2. DALL-E 2 is just a few extra refinements. But yeah, there's a few different ways we can do this. And so I just want to talk briefly about how they work. If you want to try glide, their very filtered small model, here's a little link. But yeah, let's just run through one by one the three ways that the glide paper tries to add this capability. So the first one is just conditioning on the text. And this is explained really well in this video. I've just got a screenshot of it here. But the idea here is, remember how we added in an embedding that represented the time step into the UNet, and it could use that as well as the image features to produce its output. We're going to do the same thing, but now we'd like to have some sort of embedding or representation of the text so that it can use that to better inform its predictions. And so in the paper, they try feeding the text through a transformer model and taking its final embedding and using that. That doesn't really work, so then they keep adding more and more. I think in the end they have all the embeddings of all the different words in the sequence of the caption, and they shove them in at a bunch of different places in the network using attention to kind of attend to all of these text samples at a bunch of different places. So really, really trying super hard to shoehorn in this text component, this text conditioning, but they still found that it was tricky because the network as it's trained still tends to rely mostly on the input image to predict the output. But with a lot of effort, they could force it to take some account of the text. So that on its own didn't seem to do amazingly, but it did produce some ability to steer the images, and you can see the results in especially some pre-glide papers that were doing this. But okay, so that one doesn't work super well. We'll see how it comes in useful later in the third technique. But as an intermediate idea, one that sprung to mind based on basically everyone using clip guidance or classifier guidance on a lot of other techniques is to say, well, can't we use another network, right? Like a classifier that can do class predictions, or even something like clip, which can take in text and compare an image to that text, can't we kind of use that to nudge the process in the right direction? And so this this guidance that they talk about is exactly that. Again, the video has some nice visual illustrations of this, but the key idea is that we take our noisy image, we use our model to make a prediction of what the noise looks like, but then we also feed the resulting image through clip, and then we say, or some other classifier, and we get the clip loss or the error with respect to each pixel, which is basically saying how might I tweak this image to match the prompt better. And then we do a little bit of that modification as well. So now instead of just using our original diffusion model to gradually remove noise, at each step we're removing some noise with the diffusion model, and then we're also tweaking the pixels of the image slightly to nudge them towards the clip prompt or the image class or whatever our guiding classifier is doing. So pretty neat trick, and again you can go and check out the Glide paper and you can see that with this clip guidance they're able to get some fairly decent results. But they still weren't satisfied because now we're relying on a whole extra model. We've got to have this separate classifier or clip model that's been trained elsewhere. It still seems a bit non-ideal. And so the third cool idea that was introduced is this idea of classifier-free guidance. And opinions are rather divided. I think it's a pretty neat trick. Other people say it's a bit of a hack. But the way this works is to say, well, we can train with our text conditioning. And we've noticed that the model doesn't pay too much attention to that. But maybe if we train sometimes with the text and sometimes without during training, then when it comes time to do the inference, what we can do is for a given step, we can produce a set of predictions without using the text. We can produce a second set of predictions with the text. And then we can kind of take the difference between them and scale that to kind of push our final predictions even further in the text direction, right? So we have one set of predictions that's just what's a plausible image given the input image, a second that says what's a plausible image given the input image and the text that describes what it should be, and then we're kind of moving from the non-text image towards the image and then even further. And that how far we go is determined by the so-called guidance scale. And you can see it in action here. I just used this open source Glide 3 or GLID 3 model. With guidance scale 0 and the prompt a skull, it doesn't really produce a skull because at each step it's producing an image without looking at the text and one with the text, and then it's ignoring the one with the text because our guidance scale is 0. Guidance scale of 1 is the same as just having the text conditioning, right? We're just looking at the one that's produced with the text added and used in those attention layers and so on. And you can see it sort of looks like a skull, but not quite. But if we increase the guidance scale, we're now at each step moving more and more in that direction of our prompt. And we get more and more extreme. Obviously, a guidance scale that's really high is just going to be pushing things out of range a lot and can get really messy. But for guidance scale of about 3 or 5, depending on what implementation you're using, this actually works really well. I think this is what the Glide paper found worked best. You can see in their appendix they have a lot of comparisons between different approaches. I think I'll have to go even further. Yeah. So they try a lot of different variants of these, and they find that the classifier-free guidance with guidance scale of 3 does really well. And so that's kind of become, if not the norm, then at least the most popular option for text guiding these diffusion models is to use this classifier-free guidance. And we'll see into the future whether this remains the case or whether we find better ways of doing that just generic text conditioning so that the model actually uses that text information more strongly. But for now, at least, this is pretty much the state of the art. And if you look at the DALI paper, this is effectively what they do. Now, they have some extra magic here in that they condition not on text from a transformer necessarily, but they use the clip embedding of the text. And then they also have this extra part that converts the clip embedding of text into what it would be if there was a clip embedding of an image. So they have this prior network. Because clip doesn't map images and text to quite the same space, they have to add this kind of conversion. And then this is what's used as conditioning information for their decoder. And so, yeah, that's the only modification there. But the decoder is still a diffusion model just like that used in Glide, actually just like that used in our notebook here. It's just trained on a lot of images, and they have this extra trick of that prior network and clip as the sort of generation of the conditioning information. And that gives them, at the moment, state-of-the-art results. Cool, so that's all you need to understand diffusion models. We're going to talk about a few final further innovations, but hopefully by now at least you can go and skim something like the GLIDE paper or any new papers coming out in the next few weeks, and you'll be able to convert the language and the vocabulary and so on back into these concepts that we've covered. So if you've got questions still, feel free to ask them in the Discord. I've linked extra resources, but my hope is that at this point we've actually got the idea that these aren't that crazy, right? They're not super complicated. There's some nuances and tricks that people have learned, but the models themselves are not actually unreachable, even for just an ordinary person like us to understand. Okay, so that's adding text guidance to these models and kind of bringing ourselves up to the state of the art in things like GLIDE. What else can we improve about these models? Because we said we had slow sampling, we can improve that. They just generated random images, we can improve that by adding these text guidance. What else can we improve? Well, one big thing is that they still take a lot of time to train, right? We've seen even trying to train our little tiny model, the original paper trained for like 12 hours. So how can we improve this? Well, one fairly recent trick is something called Latent Diffusion, right? And this is images from Comphys's Latent Diffusion model that's been released, probably one of the best open source text-to-image models at the moment. And the key trick here is that instead of doing this gradual noising process on an image, which if you think about it, a 256 by 256 by 3 channel image is a lot of information. What if we could instead work on some smaller compressed representation that we could then later decode into an image? And if that rings a bell, we've seen that kind of thing with autoencoder models like VQGAN or VQVAE or any actually autoencoder model. So we can now take an image, encode it with the autoencoder into the latent space and get a latent representation. And that's our X0. And then we can gradually add noise to that latent representation and train a model to do the denoising again on this latent representation, which is usually much smaller than the input image. And when we're done, we can decode that back and see what the output image looks like. And so by working in this more sort of low-dimensional latent space, we just reduce the amount of compute required, right? And so I think latent diffusion, probably about 10 times less compute than the equivalent just on raw images diffusion model. So that's a neat way to do that. You can go and read the Comphys Latent Diffusion. The repo has lots of good information and links to a paper. And you can also play with this directly as a Hugging Face space, set up by actually a current student of this course. Really great demo of this latent diffusion model. Highly recommend going and playing with that. It's really, really amazing what it can do in this text-to-image domain. Okay, so that's a great improvement. We've reduced the training cost. What else can we fix? Well, arguably, one limitation of these text-to-image models is that to train them, we need images with associated captions, right? And you could say, well, there's lots of that available now. There wasn't a few years ago, but there's been some great data sets released. But sometimes you still want to train on data that doesn't have captions. And so you might feel that that's a hopeless cause, but along comes Klube-conditioned latent diffusion. And the key idea here, if you remember from our recap lesson, lesson 5, Klube maps images and text to roughly the same space. And so if we can use a Klube embedding as our conditioning, we're effectively doing something similar to DALI, but we're skipping this whole prior network jazz, and we're just saying, if we encode an image, we get an embedding that we can use as conditioning. And if we encode text, we're probably going to get a very similar embedding. And so during training, right, we can feed in just images, and we can condition on the Klube embedding of that image. And then at inference time, we can feed in some text, get the embedding of that text, and feed that into the network as if it was the image embedding. And hopefully, thanks to Klube, the image embedding of a training example of a snowy landscape is going to be very similar to the text embedding of our prompt, a winter landscape. And the resulting images are then going to fit that prompt. And somehow, magically, it works, right? This is examples from a Klube-conditioned latent diffusion model I fine-tuned on the WikiArt dataset, which doesn't have captions. So you can read more about that in the blog post. There's a little demo if you'd like to try it out. And it's pretty neat. It only does well at things that are kind of in the domain of the data set. So it's probably overfit a little bit to that, lost a lot of more general information, but it makes pretty pictures. And the magic of this CLUBE-conditioned latent diffusion is that we don't need captions to train. So that's one final neat little addition. I think we're done. Every day there's new research coming out. Just I think a few days before this lesson first dropped, NVIDIA showed off their, what do they call it? Denoising diffusion GANs that are able to do effectively like 2 or 3 steps as opposed to 25, 50, 1,000, and even more efficiently learn to do this denoising process. Some people are like, isn't this just a GAN at this stage? But they show how mathematically it's still incorporating some great ideas from diffusion models. You can go and check out the paper. But I guess what I'm saying is that this field is rapidly evolving. Another 2 papers down the line, we'll see faster, quicker training, even more beautiful images, and so on. But hopefully by the end of this lesson today, you've at least got the vocab and the understanding to go and take a look at something like that and see why it's so exciting and why it does better. So that's it. Thanks to Jimmy on the Discord for sharing a bunch of extra resources. Some of these are just big compilations of all the papers related to diffusion. So if you are excited to really go back into the history of score-based models and how this all arose, you can check those out. But otherwise, we're pretty much done. I do have one final little addendum that I'd like to talk about. It's unrelated. But I just thought it would be worth chatting at this stage since we're looking at these large models. They can often take a while to train. Just giving a quick little look at how we might go from experimenting in a collab where things run, for an hour max or whatever. How do we take this and formalize this and track it? And basically my main piece of advice is to say, once you're happy with your initial experiments in the model, formalize it, put all your parameters in one place, make it something that you can call as a script, and then perhaps set up something like weights and biases or another logging framework where you can do something like, every iteration you log the loss, single line of code. Every 100 iterations or 1,000 iterations, you log some demo images. And what it gives you is a situation like this where you can now really dig in and explore, how the generations change over time, how different models compare to each other. You can go and look at your table and say, what's the difference between this one and this one? Okay, I used a different batch size and I increase my learning rate or I decrease my learning rate. You can do a lot more than that, keep track of all of the internal gradients and so on. But yeah, it just means that suddenly you have artifacts of exactly what parameters you use during training. You have comparisons between different models. You can see which parameters might work best. And you have a permanent record. You can even store the model itself, the trained model, so that if you're wanting to invite someone else onto the project or revisit it later, you're not saying now which learning rate was best again, flipping through your notebook and trying to see the history of edits to a single cell. You can say, comparing Faithful Moon to Valiant Deluge, and you can rename this. This one was a much lower learning rate. Okay, great. And I can see that didn't work as well. So in future examples, maybe I'll increase that. So just wanted to put it out there as a final little PS. If you're playing with these diffusion models and you're trying to train one, overnight on a big GPU machine in the cloud, you probably don't want to just be relying on, a notebook interface where you're trying to remember what parameters you used. And it's worth just spending that extra, 20 minutes to set up logging, make everything nice, keep track of your parameters. And there's a huge payoff in the end. So that's my little PS. Otherwise, I hope you've enjoyed the lesson. As always, feedback and questions are welcome in the Discord. You can get to that via our GitHub link. There's an invite there that should still be current. If not, please reach out. And if you make anything cool, we always like to see that. So pop it into projects and sharing. But otherwise, we'll see you next week where we're going to retreat from these big, scary models back to, I think I call it the quirky backwaters, where we'll play with some smaller, more niche ideas in generative modeling and hopefully have a bit of fun, again, making some pretty pictures without worrying too much about keeping up with OpenAI and Microsoft research. Thanks so much for watching, and we'll see you next week.